Hello and welcome to today's revision session on electricity, in particular the basics of electricity, which is found in the GCSE Combined Science and Separate Science physics. So the first topic we're going to look at in this revision session is standard circuit diagram symbols. So electrons can be made to move in an electrical current by having kinetic energy when they're attached to a power source such as a battery or a cell or a power pack, which provides a potential difference. So electrical devices are devices found in electrical circuits that convert electrical energy into other energy stores. So the energy starts as a chemical energy store in the battery or the cell. The battery then puts energy into the electrical circuit, and work is then done via the electrical circuit via electrical current. So work is done when charge is moved around our electrical circuit. The energy is then outputted as a store of the circuit. In this case, there's a light bulb. Now remember, energy cannot be created, it cannot be destroyed. This means the energy supplied by the battery equals the energy outputted by the outputs of the circuit, but this will be a closed system. But most electrical circuits are actually open systems, so this means some energy is dissipated to the surroundings through the wire, and this makes the circuit hot. So in reality, the energy supplied is equal to the energy lost through the wires plus the energy outputted from the output. Now eventually all of the energy supplied by the battery or the cell is dissipated into the internal energy store of the surroundings. So devices which transfer electrical energy into other energy stores include resistors, include light bulbs, include rheostats, include fuses, but we can display these particular components in physics by using electrical circuit symbols. So it's important to note that we do this because irrespective of the person's native language, these diagrams and these symbols can be understood across the entire world. And in addition, we use electrical symbols as they're easier to draw and they're less open to interpretation. So let's have a look at a few of these electrical circuit symbols. You've got the cell, which supplies electrical energy to the circuit, with the larger terminal on the left being the positive one. You've got the battery, which supplies electrical energy to the circuit and it's made from one cell. You've got the lamp or the bulb or the filament, which is the device which converts the energy stored into light. You've got a switch, which is a device that allows current to flow when it's on the closed position. You've got a resistor, which restricts the flow of current, for example, to limit the current passing through an LED. You've got a variable resistor or rheostat, which is used to control the current in a circuit. You've got a fuse, which melts if the current in a device becomes dangerously high. You've got a diode, which is a device which only allows current to flow in one direction. You've got a voltmeter, which is used to measure potential difference in the circuit. An ammeter, which is used to measure current in the circuit. An LED, a light-dependent resistor, which is a device used to convert brightness to resistance. A loudspeaker, which converts the energy stored from electrical to sound. A thermistor, which converts temperature to resistance. Now we've got to be able to draw correct diagrams with these circuit symbols. So we use these as it allows electricians and engineers from all around the world to understand the electronics of a device even if they don't understand the language of the country. So this is important as you can then assess the dangers of the circuit and the requirements of the circuit. So a circuit diagram shows you how the components in a circuit are connected together. So it allows you to work out the layout of your electrical circuit as shown in the following examples. Now, here's an example of a simple series circuit diagram. Now a series circuit is a circuit with one big loop. Now it's important to note that in a series circuit the current is constant in the loop, but in the potential difference is split over the outputs in your circuit. Now here's an example of a simple parallel circuit diagram. The voltmeter is parallel to the bulb. Now a parallel circuit is a circuit with more than one loop. So in a parallel circuit the potential difference is the same in each path, yet in a series circuit the current splits across each path. So there's the following rules when we look at drawing circuit diagrams. You always use a pencil and a ruler. You draw these diagrams clearly and make them big. You always ensure the circuits are completed. You ensure the wires are drawn as straight lines and the current flows from the large line of the battery around to the smaller line. So here the current starts at the large line of the cell and goes to the smaller line. Now in the circuit diagram the current current flows from the positive terminal of a battery to the negative terminal. Now we call this conventional current, and the lines are drawn with the pencil as they're straight lines and they are completed. So let's now consider charging current. So let's consider the inside of a metal wire such as a copper. So metal wires are full of free electrons. Free electrons are electrons that are not bound, not included to any nucleus or ions. So the greater the amount of free electrons, the better the electrical conductor a material is. So electrons are very small particles that have a negative charge. Now a charge is a fundamental property of material like colour is. Now electricity or electrical energy is the kinetic energy of electrons moving in a particular direction. Electricity in metal wires occurs when the free electrons in the metallic structure are all moving in the same direction. Now charge is the property of the electron or any particle that allows it to move in a current. If an object has an overall charge, it can be moved in a current. Electrons are negatively charged and can be moved in a current. Now electrons have a negative charge, so therefore can move in a current. Now protons and positive metal ions could also move in a current, but the forces needed to do this is too large to achieve at room temperature because these particles are very, very big. Now we can place a potential difference through the wire which can make the electrons want to move in a particular direction. Now the electrons will want to move to the opposite charge, which is a positive, and move away from the same charge, which is a negative. Now our potential difference which will cause electrons to move in the same direction is provided by the battery or the power pack or what the particular power source of our circuit is. So for an electrical circuit to flow, so if electrical current to flow in a circuit, the circuit must be closed and contain a source of potential difference. A potential difference causes a current to flow when there is a complete circuit. So the potential difference is the ability for the free electrons to do work. It's the amount of work done per unit charge in the circuit. So the potential difference is the energy needed or the work done to move charged particles in a current per unit charge, which is provided by the battery or the power source of our circuit. So batteries can act as a source of potential difference. The mains potential difference, which is what occurs when you plug something into the mains, is 230 volts. So current is the movement or the flow of electrons around the circuit. The more electrons that flow, the larger the current. The quicker the electrons that flow, the larger the current, and current is measured in amperes. So the negative electrons want to move to the positive charge as they are negatively charged, and so all move in the same direction. Now when the free electrons or any charged particles move around the circuit, they will hit the metal ions and each other. This will reduce how quickly the free electrons move, and this is going to reduce the current. This effect is called resistance. So the electrons collide with the metal ions and the electrons slow down. So the electrons knock into the metal ions, slow down, lowering the current, and this is resistance. The more the blocking of the free electrons moving, then the more the resistance. And there are many ways to do this, like increase the number of metal ions, make the metal ions vibrate more, or decrease the space between the metal ions. So when the free electrons hit into those metal ions, they'll reduce their speed, and that is what's going on with resistance. So you can summarize these concepts with the following picture. So the charge is the quantity that moves in the wire, the current moves how the charge moves through the material, the potential difference measures the energy needed to move the charge in the material, and the resistance measures the difficulty the charge have in flowing in a material. The higher the resistance, the lower the current, as the charge finds it more difficult to move. The higher the resistance, the higher the potential difference, as more energy is needed to move the charge through the material. So like we said before, current is the movement or flow of charge around the circuit. So what will happen is a potential difference across a complete circuit will cause a current to flow. So it will cause the electrons to flow in the same direction in the circuit. The current is how quickly the electrons move in the circuit. It's the rate at which the electrons move in the circuit. Now electrons only move due to their charge as they're attracted to the positive. So the current is the rate at which charge will move in a circuit. So current can be worked out with the following equation. Current in amperes is equal to charge in coulomb over time in seconds. So current is the same in any part of a series circuit. The electrons do not speed up, they do not slow down, but current will split when it encounters a junction. Now the electrons will split equally about which path to take. Now this equation should be memorized for your examination. So let's now look at current, resistance and potential difference. So for electrical charge to flow through a closed circuit, the circuit must include a source of potential difference. So a source of potential difference causes an imbalance of charge to be found in a conductor or an electrical circuit. circuit. So examples of potential difference sources include batteries and the main supply. Now another name for potential difference is voltage. So a potential difference in a closed circuit causes a current to flow in the circuit. So we can have a look at the following equation. If potential difference is the work done per charge to move a charge around an electrical circuit, we can say that potential difference in volts is equal to the work done in joules divided by the charge measured in coulombs. Now the potential difference can be considered the driving force pushing the charge, which is the electrons, around the circuit. Now the potential difference in a closed loop of an electrical circuit has an overall value of 0. So the potential difference put into the circuit equals the potential difference coming out of the circuit. This is because energy cannot be created, cannot be destroyed, it can only be transferred in an electrical circuit. So the current through a component depends on both the resistance of the component and the potential difference across the component. This is because the potential difference provides the energy to drive the electrons around the circuit. This is because the resistance provides an impedance to prevent the electrons moving around the circuit. So we can link these values together with an equation. Potential difference is equal to current times by resistance, where potential difference is measured in volts, current is measured in amperes, and resistance is measured in ohms, which you can symbolize with the equation V equals I times by R. The greater the resistance of the component, the smaller the current for a given potential difference across the component. The lower the resistance of the component, the higher the current for a given potential difference across the component. Now when the free electrons move around the circuit, they will hit those metal ions and they will then slow the electrons down. This effect is resistance. So the electrons collide with the metal ions will slow them down. So like we said before, there are many different ways in which you can do this. Now previously we've looked at what resistance is, but now we can look at how to calculate it. And this is calculated from the law found by a very famous physicist called George Ohm, which was called Ohm's law. So Ohm realized what the concept of resistance was. Resistance is the difficulty charged particles have when they try to flow in a current. So resistance is caused by the collisions between the charged particles and the metal ions in an electrical wire. And you can calculate it with the equation resistance is equal to potential difference divided by current. And we named the unit of resistance after George Ohm, which is given the resistance ohms. So when an object has a constant resistance, current and potential difference are directly proportional. So directly proportional means the two factors change with the same rate, i.e. when one doubles, the other doubles. So when this happens, we say the device obeys Ohm's law. We say that when this happens, the device is an ohmic component. So Ohm's law can only be achieved when there's a constant temperature, as this can affect how many collisions occur every single second. So Ohm's law can only be achieved if the device has a constant temperature. So we say that resistance is equal to potential difference divided by current, and for this to occur, the device must be following Ohm's law. So let's have a look at an example calculation. A 10-volt bulb has a 2.0 amps of current going through it. What is the resistance? So the resistance is going to be 10 volts divided by 2 amps, which equals to 5 ohms. So we can actually also calculate the resistance experimentally by carrying out the following method. So it's an ammeter is placed in series with the object, and the ammeter is used to measure the current through the resistor. You then have a voltmeter is used to measure the potential difference across the object. The variable resistor is then used to adjust the current and potential difference, and you investigate the variation of current with potential difference by adjusting it in predetermined steps. And then each step, the current and potential difference are recorded from the voltmeter and the ammeter, and the measurements are plotted on a graph. So you can see it as the following. So the gradient of the line is the resistance of the circuit. Now this must have a y-intercept of 0, as without a potential difference there is no current. Now it's a straight line through the origin because it's shown a directly proportional relationship, because current and potential difference are directly proportional. If the line was not straight and did not go through the origin, the material does not follow Ohm's law and is not an ohmic component. So the higher the gradient, the higher the resistance. The lower the gradient, the lower the resistance. And a straight line gives a constant gradient, so the resistance of the material would be constant. Now if we measure the current with an ammeter. Now an ammeter is a measuring device with theoretically no resistance and is placed in series in a circuit. Now we measure potential difference with a voltmeter, which is a measuring device with theoretically infinite resistance and is placed in parallel with the device being measured, VIP, voltmeter in parallel. So we place our ammeter in series. Now we place our ammeter in series as it allows us to measure the flow of electrons. So only one point is needed in a circuit to measure how quickly the electrons are flowing. So this means the ammeter can be placed into a circuit in a series formation, but ammeters have to have a low resistance, as therefore it doesn't affect the current flow in which it is measuring. The voltmeter is placed in parallel in an electrical circuit because the voltmeter measures the energy difference over 2 points of the circuit per charge, so it needs to be in parallel. So you will calculate the difference of energy between two places in a circuit and then divide it by the charge to work out your potential difference. So this means the voltmeter can be placed in a circuit in a parallel formation, but it has to be placed in parallel with the device it is measuring, nothing else. So as it's placed in parallel, it has to have a high resistance so it doesn't affect the current flow of the circuit. Now finally, we can do an investigation to look at how the length of the electrical wire affects the amount of resistance in the wire. So you're finding the link between resistance and length of wire. So you'll need the following equipment: multimeters, crocodile clips, and a wire taped on a 1 meter ruler. So therefore you would get this particular equipment and you get a nichrome wire. So therefore you then get a meter ruler. You then pull out your 1 meter wire through your ruler, make sure it's pulled straight and there are no kinks in it. You get a roll of sellotape and you tape down the wires to the two ends of the ruler. You then cut down the wire and secure it more securely with more sellotape. You then get a multimeter, which is a measuring device which can measure many different quantities as shown here, and you get crocodile clips to the end of the wires. You then attach the wires to the bottom two holes of the multimeter, but if it's not connected, the wires would show a large amount of resistance, which is represented by 1 on the device. You then attach one wire to the nichrome with 0 centimeters of the ruler. Now don't affect the multimeter as it can affect your results. You then attach the other wire to the nichrome wire at 5 centimeters and measure the resistance. So you ensure the clips aren't touching, otherwise it would create a short circuit, but don't move the multimeter as it could actually affect the results. So you then move the 5 centimeter clip to 10 centimeters and measure the resistance, and you do this every 5 centimeters up to 100 centimeters, and then you can find out the relationship between length and resistance. And here are some results which linking together the length of the wire and the resistance generated, which you can then plot on a graph of length against resistance. Now the line of best fit should pass through the origin, because the resistance of a wire and the length of a wire are directly proportional. If the line of origin does not pass through the origin, then there's a systematic error in the investigation. This could be the resistance found in the electrical connections of the voltmeter, or it could be that the length of the wire is being measured incorrectly due to the first clip not being exactly at 0 centimeters. So let's summarize what we've learned about in electricity in this revision session. We've learned about the different standard electrical symbols and how to use them in circuit diagrams. That for electrical charge to flow through a closed circuit, the circuit must include a source of potential difference. That electrical current is the flow of electrical charge, and the size of electrical current is the rate of the flow of the electrical charge, where charge of flow equals current times by time, and current has the same value at any point in a closed loop. The current I through a component depends on both the resistance R of the component and the potential difference V across the component. So the greater the resistance of the component, the smaller the current for a given potential difference, and our equation is potential difference equals current times by resistance. Now you should also be able to explain that for some resistors the value of R remains constant, but in others it can change as the current changes. The current through an ohmic conductor is directly proportional to the potential difference across the conductor. This means the resistance remains constant as the current changes. And you should also be able to, where required practical 15, use a circuit diagram and check the appropriate circuits to investigate the factors affecting the resistance, the length of a wire at constant temperature. So I hope you've enjoyed today's revision session, which has been looking at the basics of electricity in GCSE Combined Science and GCSE Separate Science Physics. Thank you very much for watching and have a lovely day.